Hello everyone. In this video we're going to go over Chapter 1's practice test. Right. So our very first question here is looking at the number of times children hit a stuffed toy after watching a nature video, or in a video of an adult hitting a stuffed toy. We want to know, is the measure of aggression continuous or discrete? So this would be a discrete measure, and it's discrete because there's nothing that occurs between any two categories. So a kid could hit a toy 1, 2, 3, or 4 times, but fractions don't make sense, decimals don't make sense, and for that reason it's discrete. Right. Question 2, we're looking at the same variable. Now we're looking at whether or not the scale of measurement is nominal, ordinal, or interval ratio. Okay. So since we're looking at the number of times children hit a toy, this is interval ratio data. We have categories, the categories are in order, and the distance between the different categories are all equivalent, right? The distance between a 1 and a 2 is the same as the distance between a 3 and a 4, right? That makes it an interval ratio scale of measurement. Okay. Number 3, we're looking at the same scenario, but now we're asking about the independent variable and the dependent variable. So in this case, we are manipulating, as researchers, what kind of video they watch, either a nature video or a video of an adult hitting a toy, and then measuring the number of times children hit the toy. So our independent variable is the variable that is manipulated, which is the video they watched. The dependent variable is the number of times the child hit the stuffed toys. Okay. All right, moving on to number 4. Now we're looking at a frequency distribution. Okay. So we have here X's and frequencies. X's are the categories or the scores, and the frequencies are the number of children in each of those categories. Okay. So in this example, we have kids hit the doll either 1, 2, 3, 4, or 5 times, right, listed here. And then the frequencies represent how many people are in each category. We have 0 kids who hit the doll once, 1 hit the doll twice, 7 hit the doll 3 times, and so forth. And we're asking you what's the best description of the shape of the distribution. Right? So in this case, we'd have very few scores at the low end, and we have quite a few scores at the high end. Right? So this would be a negatively skewed distribution, right? So if I were drawing this out, I would have more scores, like 14. If I go 1, 2, 3, 4, 5 are my categories. And then I have 14 people with scores of 5. I have 8 people with scores of 4, I have 7 people with scores of 3, and I'm just ballparking this graph as we go, and 1, 2, and 1, 1, right? So that would be a negatively skewed distribution there. Okay. Question 5, we're still working with this same set of data, and we want to know how many children watched the video of an adult hitting a stuffed toy. Right? So if you look at this frequency distribution, we have 0 kids in category 1, 1 in category 2, 7 in category 3, and so forth. So you just need to add up these frequencies, right? So you have 14 plus 8 plus 7 plus 1, right? Or we have, was it 15, 16, 30 people, right? If we add up the frequencies. That's always how you can figure out how many people responded in that data set. For video number 6, we want to know how many children hit the stuffed toy 1 time. So in terms of X of 1, we have 0 people. So 0 kids hit the doll 1 time, or hit the toy 1 time. For question 7, we want to know what percentage of children hit the stuffed toy 4 times. Okay, so this one you need to do a little bit of work to get. Oops, let me clear off my whiteboard here. I'm trying to clear it off. Delete. Yeah. Okay, so if we're looking at the number of kids who hit the toy 4 times, it's 8, right? So we have 8 kids that hit the doll 4 times, and there were a total of 30 kids. Right? So what you're going to need to do is just divide this, right? So you take 8 divided by 30, and that gives you 0.266, right? And so if I turn that into a percentage, I'm going to get, I guess, 26.6%, right? Or the 26.67. This would have been 2.666 here. Okay. So to turn it into a percentage, you divide by the total number of people in the data set. Okay, next we'll have more examples of nominal ordinal interval ratio. And this one we have wondering if men or women display more anger, and record the gender of each participant. So gender is nominal. We're just putting people into categories, or they're in pre-existing categories, and there's no numerical, like you can label people as 1 for male, 2 for female, but that doesn't mean that 1 or 2 is better or worse than another. There's no quantity or quality indicated by those numbers. Right. Next, question 9 asks you which of the following variables is ordinal. So let's start with the amount of money you have in your wallet. So in this case, amount of money you have in a wallet would be interval ratio, right? Because the distance between categories is equivalent, right? So if I'm talking about $1 versus $2, the distance between $1 and $2 is exactly $1, right? It's just the $1 always means $1. Or if you're thinking about in pennies, 1 penny always means 1 penny. The distance between those categories is always equivalent. If I look at t-shirt sizes, small, medium, and large, that's a good example of ordinal data, right? That we know that medium is bigger than a small and a large is bigger than a medium, but we don't know by how much. The distance between those categories might not be the same. Okay? If we look at temperature in a room measured in degrees Fahrenheit, this would be an example of an interval ratio scale, okay? Because the distances between, like, even if you think about a thermometer, like the tick marks on a thermometer are all equally spaced. Each degree, 1 degree increase means the exact same amount each time. Finally, we have numbers on football players' jerseys. These numbers don't indicate, you can't like put people in order based on their jersey number, right? It doesn't, the numbers don't indicate quantity or quality of player. Okay, number 10, we're looking at participants are asked to submerge their arm in a bucket of water that's really cold and keep it there as long as possible. And then we're looking at how long they keep their arm in the bucket. So that would be interval ratio, right? Length of time, 1 minute is always 1 minute, right? Or 1 second is always 1 second. The size of a minute or second never changes, right? That would be interval ratio because those intervals are equal. And then next we're looking at the same variable, but now we want to know if it's continuous or discrete. And this would be a continuous measure. Looking at time, fractions, decimals do make sense. And so continuous there. All right, next we have number 12. We have Dr. Jackson has asked all 42 of her patients if they're satisfied with their medical appointment. And they rated on a 7-point scale, and she finds that the average response was 42. Right? And so in this case, we're asking you the purpose of this survey, right? And the purpose of the survey is never sampling error, right? It's either a descriptive or inferential purpose there. Okay? In this particular case, this is going to be the purpose of descriptive. She wants to look at her patients, only her patients, and wants to know how satisfied her patients are. She's not trying to figure out how satisfied all patients are of different doctors, just her particular patients, and she looked at all of her patients. So that's descriptive. Number 13, a counselor wants to know how prevalent binge drinking is on campus of 3,500 people and sends an anonymous survey to a randomly selected group of 300 students, right? And so they find that the average number of binge drinking episodes per week is 1.2. And the question is that a statistic or a parameter? Statistics are values that describe samples. Parameters are values that describe populations. She took a sample of 300 people from the greater population. So this is a sample statistic. Okay. Next, A counselor wants to know how prevalent binge drinking is. Same example as before. And now we're saying, suppose that like all 300 people returned the survey, right? Instead of, originally we say that a total of 195 were returned and then the average was 1.2. What if we received data from all 300? It doesn't change anything. The average number would still be a statistic because you're looking at a subsample of that overall 3,500 people. It would only be a parameter if you considered the entire college campus of 3,500 people a population and all 3,500 people responded to the survey and you received an answer from them. Okay, number 15 here is getting at the same idea. Values computed from samples are called statistics, while values computed from populations are called parameters. All right, so now looking at, number 16 here. The question is, which of the following terms is defined as the difference between a sample statistic and a population parameter? That's sampling error. So our definition of sampling error is that sample statistics are not identical typically to population parameters, and the difference between them is referred to sampling error. For number 17, this is asking about the 4 pillars of scientific reasoning we introduced into the first chapter. And our 4 pillars are hypothesis testing with continuous p-values, describing practical importance with effect size, and estimating population parameters with confidence intervals. It's not determining the scale of measurement. The last pillar has to do with scientific research and methodology. So we haven't done much with this yet. We're going to come back to this later in the class. This is just a reminder of what we started introducing in Chapter 1. All right, next for number 18, an instructor records the primary academic major of each student in her class. What type of graph should be used? So academic major would be nominal data. Whenever you have nominal data, it's best to use a bar graph to indicate that nothing exists between any 2 given categories. Remember, a bar graph is the kind of graph where the bars do not touch. All right, number 19 is asking about some terminology about distributions. And over on the right here, you can see I drew 3 distributions. The black one is a normal distribution, right? It is bell-shaped curve. A leptokurtic distribution is more peaked. It's the red one. And the platykurtic distributions are flatter, right? That is the blue one there. Number 20. Okay, so starting with number 20, we're going to be analyzing data that you're going to need to download and enter into Jamovi. Is what we're using this semester, but you could do this really with any software package. And what we're looking at here is people's answers on a vocabulary test. They're asked 10 vocabulary questions, and we want to know the number that they got correct. So I'm going to open this up in Jamovi. Open my data file, and I have it just saved to my downloads folder. You're going to have to find where yours is downloaded. Okay. So in this case, I need to start by creating a frequency distribution table. I'm going to click on Exploration and click on Descriptives and move Vocabulary Test over into the Variables box. And then I want to get a frequency distribution table, so I'm going to click on the Frequency Tables box. Okay. So first thing you can note here is the N is the sample size. We have 1,387 people who responded to this survey. Okay. So if you go back to this question, the first question is how many people responded to the survey, and so we have in this example we have 1,387. Okay. All right. Next, we want to know how many people got 10 questions right. So we want to know how many people got 10 questions right. We're going to go back to our frequency distribution table that we already created here. Sorry. Let me move that over. And so we want to know how many people got 10 right. We have 67 people got 10 right. So I have 67 people got 10 right on that distribution. And that represents 4.831% of the people of the 1,387, right? If you divide 67 by 1387. All right, moving on. Next is what percentage of people got all 10 questions right, which we just answered that question. Number 23, what percentage of people answered 2 or fewer questions correctly? Okay. So here, I want to look at the number of people who got 2 or fewer correct. So I'm going to look at level 2. We have 53 people got 2 or fewer correct, or sorry, got 2 correct. 22 got 1 correct, and 4 got 0 correct. So I can look at the cumulative percentage column, and that will give me the percent of people who have scores at or below a given category. So 5.696% of people had scores of 2 or lower. Okay. Had we asked about how many people had scores of 7 or lower, it would have been 76.208%. All right, so in this case, again, you were looking at 2 or fewer, and so the answer is 5.696 or 5.70 for rounding. All right, number 24, we're looking at what percentage of people answered fewer than 2 questions correctly. So in this case, we have fewer than 2 questions. You're going to look at 1 or lower. That would be 1.85 or 875%. Or it's 1.87 on question 24. All right, next, we're going to graph the data. And to graph it, we're going to click on Plots. And I'm going to look at a bar plot here, because my data are discrete, so a bar plot is more appropriate than a histogram. Right? And so if we look here at our data, this looks, fairly normally distributed. Right? There's a slight, I suppose, skew to the negative side, but it's really fairly, very slightly negatively skewed. Right? It's not perfectly normal, very slightly. All right, and that is all for this quiz. Okay, so we're going to move on then to the next one.